Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the grand intellectual theatre of the late 19th century, a period rife with the consolidation of classical physics and the rigorous formalization of analysis, few documents stand as such a radical departure and profound genesis as Georg Cantor's 1884 treatise, Grundlagen einer allgemeinen Mannigfaltigkeitslehre, or Foundations of a General Theory of Manifolds. This singular work, published in Leipzig and championed by the perspicacious editor Gerst Mittag Leffler for his journal Acta Mathematica, represented a moment of profound schism and creation. It was a declaration of mathematical independence, a philosophical polemic, and the technical blueprint for a new cosmos of number and form. The paper did far more than introduce novel concepts. It sought to redefine the very bedrock of mathematical reality, providing a language for the infinite that was born from a concrete analytical struggle. In its pages, Cantor, a figure of immense intellectual courage and tragic vulnerability, wrestled with the fundamental structure of the continuum, and in his victory, bequeathed to the 20th century the twin pillars of transfinite set theory and point set topology, forever altering the landscape of pure mathematics. The intellectual crucible from which the Grundlagen emerged was the demanding field of real analysis, specifically the study of trigonometric series. Cantor's own early research, building upon the work of Bernhard Riemann and Heinrich Eduard Hein, concerned the uniqueness of the representation of a function, a Fourier series. This investigation led him to consider exceptional sets of points where the series might fail to converge. These sets were often bizarre, defying simple geometric or algebraic description. They were dust-like, scattered across the real line in intricate patterns. To understand them, to classify them, Cantor required a new tool, a new microscope for peering into the fine structure of the continuum itself. The existing mathematical vocabulary, rooted in geometry and algebra, proved wholly insufficient for this task. The challenge was exacerbated by the new standards of rigor being established by contemporaries like Karl Weierstrass and Richard Dedekind's 1872 work, Statistik under rationale Zahlen, which defined real numbers through the mechanism of cuts in the rational numbers, provided a solid foundation for the continuum but simultaneously highlighted the abyss of complexity residing within it. Cantor recognized that to tame the strange beasts lurking in the exceptions of Fourier analysis we needed a general theory of point sets, or Punktmengen, and this required a conceptual framework of unprecedented abstraction. Before unveiling his mathematical innovations, Cantor understood the necessity of erecting a philosophical bastion. The first and most overtly polemical part of the Grundlagen is a sophisticated defense of the freedom of mathematical creation. Facing the impending and ferocious opposition of the powerful Berlin school, particularly the archfinitist Leopold Krünker, Cantor articulated a crucial distinction. He posited that mathematical concepts possess an intrasubjective or immanent reality, meaning they are internally consistent and free from contradiction within the logical structure of mathematics itself. Their connection to the external, physical world, their transient reality, was a secondary concern. This powerful philosophical maneuver granted mathematics an autonomous existence, freeing it from the obligation to model the perceptible world. It was a direct challenge to the prevailing intuitionist and formalist sensibilities, arguing that as long as a concept was logically sound, it had a right to exist. Within this defense, he made his most audacious claim the legitimacy of the actual infinite. He argued against the Aristotelian tradition, which permitted only a potential infinity, a process of endless becoming. Cantor contended that infinite sets could be conceived as completed, unitary objects, a totality that he termed the actual unendlich. This was the philosophical key that would unlock the transfinite. For Krünker, who famously quipped that God made the integers and all else is the work of man, this was pure theology, a dangerous deviation into fantasy. For Cantor, it was the necessary conceptual ground upon which his new mathematics would be built. The Grundlagen was thus a gauntlet thrown down, a declaration that mathematicians were creators of intelligible worlds, their primary allegiance owed to consistency, an argument whose force was required to shield the radical ideas of. With this philosophical shield in place, Cantor proceeded to the mathematical core of his work, a systematic exploration of the structure of point sets on the real line. The central engine of his analysis is the deceptively simple operation of the derived set. For any given set of points P, Cantor defined its derived set, which he denoted P', as the set of all its limit points. A limit point of P is a point such that any neighbourhood around it, however small, contains at least one point from P distinct from itself. This operator, P', was a tool of immense power. Applying it to a set could be seen as stripping away its isolated points, leaving behind a more condensed, more essential skeleton. Cantor immediately recognized the analytical potential of iterating this process. One could form the second derived set, P', which is the derived set of P', then P', and so on. For many simple sets, this process terminates quickly. For a finite set of points, its first derived set is the empty set. For other sets, the process might continue for a specific number of steps before vanishing. This iterative derivation provided a means of classifying the complexity of a point set. The number of steps required to exhaust the set to emptiness became a measure of its structural intricacy. This iterative process, however, led Cantor to the precipice of a profound discovery. What of sets so complex that the derivation process continues indefinitely? Consider a set for which P to the power of n, the nth-derived set, is non-empty for every finite integer n. The existing number system had no symbol to mark the end of this infinite sequence of operations. It is here that Cantor made his most celebrated conceptual leap, a move of breathtaking originality. He invented a new number to represent the first infinite stage of this process. He called this number omega, the first transfinite ordinal. The set P to the power of omega was defined as the intersection of all the finite derived sets, from P to the power of 1, P to the power of 2, onwards. This was more than a mere notational convenience, it was the birth of a new arithmetic. Having reached omega, the process could continue. One could take the derived set of P to the power of omega to obtain P to the power of omega plus 1, then P to the power of omega plus 2, and so forth, leading eventually to P to the power of omega times 2, and onwards. Cantor had uncovered an entire, well-ordered hierarchy of infinities, a transfinite sequence of numbers that extended the natural numbers into a realm previously confined to theological speculation. These ordinal numbers were forged in the heat of a specific analytical problem to provide a precise, exhaustive classification system for the structural complexity of point sets. Their creation was a testament to the idea that mathematical objects could be willed into existence to serve a logical, armed with this new transfinite calculus of sets. Cantor delivered one of the paper's crowning achievements, a deep structural theorem about the nature of the continuum. He introduced the concept of a perfect set, defined as a set P that is identical to its first derived set, meaning P equals P'. A perfect set is, in modern terms, a closed set with no isolated points. It is a kind of continuous dust, dense in itself. Using his machinery of derived sets and transfinite ordinals, Cantor demonstrated that any closed set of points on the real line can be uniquely decomposed into two distinct components, a perfect set and a countable set. This result, later refined by Eva Bendixson and now known as the Cantor-Bendixson theorem, was a revelation. It implied that the seemingly chaotic and infinitely varied subsets of the real line were built from two fundamental and disparate materials. There were the scattered, listable points of countable sets, and there were the dense, continuous structures of perfect sets. A stunning consequence of this was that any uncountable closed set must contain a perfect subset, and therefore must have the same cardinality as the entire continuum. This was the first profound insight into the anatomy of the real line, revealing a hidden order within its apparent complexity and providing a powerful tool for analyzing the exceptional sets that had first motivated Cantor's entire inquiry. The reception of the Grundlagen reflected the deep divisions it had carved within the mathematical community. Its publication was itself an act of intellectual courage on the part of Mittag Leffler, who recognized its revolutionary importance and published it despite the foreboding presence of Kronecker in Berlin. Cantor found an important, albeit quiet, ally in Richard Dedekind, whose own work on the foundations of number shared a similar philosophical commitment to abstract creation. The opposition, however, was vocal and venomous. Kronecker waged a relentless campaign against Cantor, both publicly and privately, denigrating his work as humbug and blocking his academic appointments. This assault, which painted Cantor's transfinite paradise as a gallery of pathological monsters, contributed profoundly to the bouts of depression that would plague Cantor for the rest of his life. Yet, the seeds planted by the Grundlagen were too fertile to be suppressed. They began to germinate throughout Europe, fundamentally reshaping the future of mathematics. The paper's point-set theory became the direct ancestor of general topology, a field that was given its modern axiomatic form by Felix Horsdorf in his monumental 1914 text, Grundzüge der Menschenlehre. Horsdorf explicitly took Cantor's concepts of limit points and derived sets, and generalized them into the abstract topological spaces we know today. Similarly, the classification of sets and the problems it raised about their size or extent laid the essential groundwork for the development of measure theory. by French mathematicians like Emile Borel and Henri Lebesgue, the very notion that one could rigorously define the length of a highly discontinuous set was a direct consequence of Cantor's program. Furthermore, the audacious introduction of the well-ordered transfinite ordinals inspired Ernst Zamilo's later work on the axiom of choice and the well-ordering theorem, which sought to place all of set theory on a firm axiomatic footing. The most resounding vindication would come later, from the most influential mathematician of the next generation, David Hilbert, in his famous 1925 address, declared, "No one shall expel us from the paradise that Cantor has created," cementing Cantor's legacy and ensuring that his transfinite universe would become a permanent and indispensable territory in the empire of modern mathematics. In conclusion, Georg Cantor's 1884 Foundations of a General Theory of Manifolds is a work whose significance transcends its specific mathematical results. Profound as they are, it stands as a pivotal document in the history of thought, marking the moment when mathematics fully embraced its power as an abstract, self-referential discipline, spurred by the concrete challenge of classifying complex sets in Fourier analysis, and have forged a new language of point sets, a new calculus of derived sets, and, most audaciously, a new universe of transfinite numbers. He defended this creation with philosophical rigor, arguing for the freedom of the mathematical mind to construct any world that adhered to the laws of logic. The paper gave birth to the field of set theory, provided the conceptual DNA for general topology and measure theory, and forever changed the meaning of infinity from a vague philosophical notion into a precise and richly structured mathematical object. While it subjected its author to immense intellectual persecution, the Grundlagen ultimately triumphed, revealing a hidden, intricate order within the continuum and opening up vast new domains of inquiry. It remains a powerful testament to one man's vision, a journey that began on the familiar real line and ended in a paradise of his own creation.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.